Now that we know how to define ionization energies, we're now going to have a look at the trends in ionization energies in the periodic table. So what I've got over here is the ionization energy. So it's the first ionization energy of the first 18 elements. And this is essentially the trend that we see in this. So in order to know that you have fully understood the trends in ionization energy, hopefully by the end of this video, you should be able to explain literally every kind of rise and dip in this graph over here. So you should be able to essentially draw this out from memory and explain what is happening at each rise and each dip. Right, so let's get started on the trends that we can see. All I've done is I've just highlighted each period. So this is period 1, which only has hydrogen and helium. Period 2, so going from lithium all the way to neon, and then we go back down to the beginning of period 3. This is period 3 over here, and then we go to period 4 over here, which hasn't been included on this graph. Okay, so this is the ionization energy for the first 3 periods. Okay, so the first 18 elements. So in terms of the kind of general trends that you can see here, as we go across a period, so as we go from hydrogen to helium, there's an increase. As we go, so when we go to the second period, when we go from lithium across to neon, as you can see, there is a general increase. Okay, we're going to ignore these dips for now. I will address them later. But as you can see, there's a general increase across the period. And as we go to period 3, again, we have a general increase. So the first trend is that across a period, we have a general increase in ionization energy. Right, when we go from the end of a period, so this is the end of period 1, when we go from helium to the beginning of period 2, which is lithium, which is the next element, you can see there is a very, very sharp decrease. So when we start a new period, we have a very sharp decrease in the ionization energy. And the same thing happens at the end of period 2 at neon, when we then go to sodium, beginning in period 3, again, there is a sharp decrease. And it's not shown over here, but at the end of period 3, when we go from argon to potassium, again, there is going to be a sharp decrease. So whenever we start a new period, we will see a sharp decrease in ionization energy. That's the second trend that you can see. The third trend is not very, very obvious on here, but it's the trend of when we go down a group. So if we go to the so group 0, which is our noble gases, so that's helium, neon, and argon. They are basically the ones at the top over here. As you can see, as we go down the group, when we go from helium to neon to argon, there is a general decrease. So there's a decrease when you go down the groups, and the same thing happens. So if I go to lithium, so group 1, from lithium to sodium, as you can see, there's been a decrease. Potassium would be even lower. Okay, so going down a group, there is a decrease in ionization energies. And let's now explain that trend there. So if we go down a group, the ionization energy decreases. And in an exam, you could be asked to explain why is it that when you go down a group, the ionization energy decreases. So if we go with noble gases, we've got helium, we've got neon, and we've got argon. Okay, helium just has 2 electrons. Okay, neon has 10 electrons. I'm going to draw them quite small. And argon, I'm just going to draw this a bit further down, has 18 electrons, like so. Okay, so in the trend for the first ionization energy, okay, as you can see, helium has a much smaller atomic radius compared to argon. Okay, so as you go down the group, the atomic radius increases. Okay, so that's the first point you should address in an exam. Okay, so as you go down a group, the atomic radius increases. Okay, remember there were three factors. So it was atomic radius, nuclear charge, and electron shielding. Because the atomic radius is increased, and you can also see it as well, the outer electron, so for this one, it'll be this one, one of these, or one of these, the outer electron, as you go down the group, is more shielded from the nucleus. Because you've got more shells, as you go down, you increase the shell number. There is increased electron shielding as you go down the group. So increased electron shielding. You can say more electron shielding as you go down the group. Any way you phrase that should be fine. So increased electron shielding as you go down. Also, as you go down the group, the nuclear charge does increase. Okay, but over here, the atomic radius increasing and the electron shielding increasing outweighs the nuclear charge increasing. Okay, so both of these factors here combined decreases the nuclear charge to the outer electron. Okay, so both the atomic radius increasing and the increase in electron shielding means there is a decrease in nuclear attraction towards the outer electron. I'm just going to use E minus for electron. Okay, so as I said, the nuclear charge does increase, but both of these here, these factors here, outweigh the increase in nuclear charge. Now, because there's a decrease in nuclear attraction towards the outer electron, as you go down the group, less energy is required to remove, am I fitting this in? Yes, I am, to remove outer electron. Okay, and these are the points that you should address in an exam question. So as you go down the group, ionization energy decreases because the atomic radius increases, and therefore you have more electron shielding. This produces a decrease in nuclear attraction towards the outer electron, and therefore as you go down the group, less energy is required to remove the outer electron, and therefore ionization energy decreases. So remember to address all these points in an exam question got to do with trends in ionization energy. So that was going down a group. If we now do the general trend across a period, so if I just go back to this, we said that across a period you have a general increase. As I said, we're going to ignore these dips for now. But across a period, you have an increase, a general increase in ionization energy. Okay, let's now explain that. So I'm not going to draw them all out, but if we go for lithium and beryllium, boron, okay. The thing to point out over here, that as you go across a period, the atomic radius decreases. Okay, so across a period, the atomic radius decreases. And the reason being, so lithium has, if I just draw this out, lithium just has 3 electrons. So lithium has 3 electrons, okay? When you go to beryllium, which has 4 electrons, because you now have an extra electron over here, that second shell gets pulled closer towards the nucleus. So as I go across, I'm just adding an electron to the same shell. So when I go across to boron, I'm just adding an electron to that same shell. Okay, and because it's being added to the same shell, that outer shell is pulled in closer towards the nucleus. So the atomic radius as we go across is decreasing. Okay, so the atomic radius decreases across a period. And also, because we are adding the electron to the same shell, okay, the electron shielding stays the same. So I'm just going to rub this out. The electron shielding stays the same. So atomic radius decreases, electron shielding stays the same because it's being added to the same shell, stays the same. Okay, but as we're going across the period, the electrons being added to the same shell, but the proton number is increasing. So lithium has a proton number of 3, 4, 5, 6, 7. So that means the number of protons are increasing. So the nuclear charge increases across the period. Okay, so nuclear charge is increasing, atomic radius is decreasing. So that means the nuclear attraction towards outer electron increases. Okay, so we get a smaller and smaller radius as we go across the period. Is getting smaller and smaller as you go across. The nuclear charge is increasing, so there's greater nuclear attraction towards the outer electron. And that means you require more energy to remove that outer electron. So as you go across, more energy required to remove outer electron. Okay, so these again are the points that you should address in an exam when it comes to trends. Okay, think about atomic radius, think about electron shielding, think about nuclear charge. Then make sure you address, has the nuclear attraction towards the outer electron increased or decreased? And therefore, what effect does that have on the amount of energy required to remove the outer electron? Okay, so this is the general increase as we go across a period. So as we go across there, across over here, and across period 3 as well. Also, based on that, you should hopefully see that helium, so helium over here is the one element in the periodic table with the highest ionization, the highest first ionization energy, because after that everything else has this kind of general decrease as you go down the periods. Okay, so helium has the highest ionization energy in the periodic table.